Okay, what we have here is Algebra 1 6.1. We are going to be solving systems of equations, but we're going to be graphing them. Or graphing systems of equations and solving them by looking at them. So, in the past, we've graphed single equations on a graph. So we've used slope-intercept form, we've used standard form, and we have been able to make a graph. Today, what we're going to do is we're going to take one or more of those equations and stack them onto the same graph, or graph them on the same graph. Maybe stacking is not the right word. And that would actually create for us a system of equations. The system of equations is when you have one or more on the same graph. Now there's a couple different types of systems, and they correspond with the chart below. So what we have here, there are two main types. Now you guys may have to highlight here, and you may have to write a couple side notes on those notes in here. But we have two different types of systems. The first one is consistent. To be consistent, guys, there has to be at least one solution, or we say the graphs intersect at a point or more. So they basically are going to, the two lines that you just graphed, two or more, are all going to touch at the same place or multiple places at the same time. Now there are two types of consistent graphs. So consistent means answers. There are solutions. Now the way I kind of think of this is that if I think I am independent, that means that I can do things all alone, right? And if I'm alone, there's only one. If I'm independent from everything else, there's only one of me. So therefore, if I am consistent, that means I have solutions. If I'm independent, I am a consistent system that has only one solution. So independent is one solution. The other one is a dependent. Dependent on the other side, we'll say the flip side of that, is that it's a consistent system, but if I'm dependent, I need others, and so that means there's an infinite amount of solutions. Infinite many solutions when we talk about a dependent system. One solution, infinite many. The only way we can get infinite many solutions with two lines is if the two lines are the same one. So when you graph them, they're on top of each other. You only see one line. The other type is that inconsistent. To be inconsistent just means that there's no solution. They never meet. And if they never meet, that must mean they are parallel. So, consistent means they meet up, they cross once or more. Inconsistent means they do not cross, they do not meet, therefore they are parallel. So, that chart that's there is just a nice way to put it all together. And when we put it all together, we have the number of solutions across the bottom here. We have the names of those and what the graphs will look like. So let's start at the graphs. Notice that these cross. They form like a crisscross there. You can see that they only touch how many times? Once, right there. That has one solution, exactly one solution. And then when we go look at it, it's consistent and it's independent. This graph right here, I only see one line. That's because both lines are in the exact same spot. It's consistent and dependent because there's an infinite amount of solutions to that problem. Now, I got to restate something here because I said something here about being parallel for the inconsistent because they are parallel lines, they never meet. But guess what? This would also be parallel lines. But a step further would be to be consistent and dependent. They're parallel and have the same y-intercept. Over here, they're independent, they're inconsistent because they're parallel and have different y-intercepts. So be mindful of that. Okay, so we're going to be graphing today. The key here, be as consistent and make some of the best looking graphs that you have ever made, because it'll help us with identifying which type of graph they are. Our first problem. I want you to graph the system, determine the number of solutions it has, and if it has one solution, you better name it. Which basically means I want you to graph it, tell me, is it consistent, inconsistent, independent, dependent? And then if it has a solution, name it. So is it 5, 7, negative 3, 2? What is it? So, look at both of our equations up here. Both of these are in what form? Standard form. So guess what? I'm going to use cover up for both of these. I'll change colors so we can keep track of them. First one, remember how to use cover up? I put a 0 in for x, so I cover it up. And then you got to solve for y. So negative y equals 2. What's y? Divide both sides by negative. So that means y is equal to negative 2. I cover up y. Let me try this. And so x is equal to 2. That's an easy one. I like that. Moving on to the purple. Cover up x. Ooh, I think I tried tricking you here. Where's the x in that problem? It's not the first term, is it? X is this one, so I'm going to cover up this one. 3y equals 9. What's y? What's y? It's 3. Put a 0 in for y. When does 2x equal 9? 4.5. And so now we can graph. Try making your lines as straight as possible. This would help us out tremendously. Make your tick marks as uniform as possible. It's not always easy, as my tick marks I think are a little bit off. Going back to red, 0, negative 2 is there, and 2, 0. Is everybody okay with those 2 points graphed? Connect them. Ooh, I have to say, that was a pretty nice line, I have to admit. Now, sometimes, guys, you're going to make your graphs, and you're going to see, now this is not the next graph, okay? I'm going to draw this for demonstration purposes only. Some of us might see this. And you'd be like, oh, they never touch. Is that true? No, wouldn't you guys agree that somewhere down here they're going to have to eventually meet up? Yes. That means you need to redraw your graph so that you can see that. Okay, so there will be times where you're going to have to look at something like that. Okay, purple. In the purple, 0, 3. 1, 2, 3. And 4.5. About there. I'll make that a little bit bigger, huh? Okay. Can I duplicate my first one? Not bad. Not bad at all. I think a little better than last time. So, how many times do they cross? Once. So this thing would be called consistent, independent. Independent. Because there's a solution right here. And what would that solution be?
Exactly 1.
What would the point actually be?
Oh,
3,
1.
1. 3, 1, it's inconsistent and it's independent. Now, what happens if you make that graph and it's slightly off? When I did this earlier, my point ended up being about here where they crossed. It was like 1.5. Well, guess what? Our graphs are not the most accurate things in the world, right? So I'm okay. What I did not see is that my lines didn't cross over here. So if you had a point that's way over here as your intersection, you did something wrong. So if I'm in the ballpark, somewhere in this area, you did something right. They don't have to be perfect on graphs. They're not the greatest thing. They're not the greatest tool, but they are great for, hey, am I on the right track? Next problem here. Hey, this one, the first equation is in what form? Slope-intercept form. Second one is in standard. Now, you can take the first one and switch it to standard, or you can take the standard and switch it to slope-intercept form. It doesn't matter. You'll get the same results. I prefer to graph it in whatever form it's in. So the first one I'll graph in slope-intercept form by plotting the y-intercept, moving slope. Second one, I will go with standard form and use the cover-up method. So, let's go with the first equation. I'll do that one in purple. Where am I starting? Where am I starting with that first equation? First one here. Where am I starting this one? -3.
You're doing great.
So is that -3 because it's my y-intercept? Now remember, this is slope. Slope's -2. It's really -2 over 1, which means I can go down 2 over 1. But that means I also can go up 2 and back 1. Those 3 dots will help me establish a line that I would like to draw that goes through those points, yeah? That's a little off, but that's okay. It's not perfect. Next, we'll go with orange. So next, I'll use the cover-up method. Put a 0 in for x, put a 0 in for y. If I put a 0 in for x, y equals -3. I think I can agree with that. Put a 0 in for y. When does 6x equal 9? Well, divide -9 by 6, right? 3 over 2? -1.5? -1.5. Hey, look at this. That's the same point as right there. 0, -3. Hey, -1.5 is right there. Now, would you guys agree that my line missed that point? But it's also missed right here. So maybe I should go back and redraw the purple line. But wait a minute. Isn't the purple line and the orange dots here, don't those seem to be all in a row? So technically, they both are the same. So this must mean that it's consistent and Ooh, dependent. It's dependent. And how many solutions then? Infinite many. Infinite many solutions. And that's all I got for you. There would be a third example. The third example would be they just are parallel. They don't meet at all. Different y-intercepts. And if that's the case, it's just inconsistent. Done. So, homework. Page 343, 27, 30, 33, and 35. Have a great day.